Right now, surrounding our solar system, there are trillions of objects older than the Earth itself. Most of them have never been seen. They drift through a vast shell of darkness, stretching nearly halfway to the nearest star, preserved almost exactly as they were when the solar system was born 4.6 billion years ago. Occasionally, one falls inward. For a few weeks or months, it grows a brilliant tail, captures the world's attention, and then disappears again into the cold. We call it a comet. For thousands of years, people feared them as omens of war, plague, and the deaths of kings. Today, scientists fear something very different because the more we study comets, the more they seem connected to every major chapter in Earth's history. They contain water, they contain complex organic molecules, some even contain amino acids, the chemical building blocks of life. One spacecraft spent 10 years chasing a comet before landing on its surface, only to discover a world unlike anything researchers expected. Another object entered our solar system from another star, accelerated as it departed, and left astronomers debating its behavior to this day. The same class of objects that may have helped make life possible has also struck Earth with enough force to reshape entire eras of our planet's history. Comets are not wandering snowballs. They are ancient archives, chemical time capsules, and some of the oldest surviving objects anywhere in the solar system. A like, a subscribe, whatever feels right. It all helps this channel reach more people who love falling asleep to the sound of the universe. Now, let's begin. From far away, your eyes would probably notice the glow first. A bright smear stretches across the darkness, seeming far larger than anything hidden inside it. We naturally assume that luminous shape is the comet itself, yet the brightest part is only a temporary veil, created during a brief encounter with sunlight rather than the object that has wandered through space for ages. At the center rests the true comet, a compact nucleus built from frozen water, dust, rocky fragments, and complex organic material locked together since the earliest days of the solar system. Some nuclei measure only about 1 kilometer, which is about zero point 0.6 miles, across. Others reach nearly 50 kilometers, which is about 31 miles. Compared with planets, they remain surprisingly small, more like uneven mountains drifting through an immense sea of darkness. As the nucleus approaches the sun, everything begins to change. Heat reaches the surface, and frozen material transforms directly into gas, escaping without first becoming liquid. This process, called sublimation, simply means solid ice becomes vapor immediately. Escaping gas carries fine dust outward, surrounding the nucleus with an enormous atmosphere known as the coma. That glowing envelope can expand to nearly 100,000 kilometers, which is about 62,137 miles, across, growing larger than the giant world of Jupiter despite surrounding such a tiny center. The familiar tail then appears. Many imagine it streaming behind the comet, like smoke trailing an aircraft. Nature follows a different design. Solar wind, a constant flow of charged particles released by the sun, pushes gas and dust away from the sun itself. Because of that pressure, the tail always points outward, no matter which direction the comet travels along its orbit. We can even separate this display into two distinct streams. One is the ion tail, formed from electrically charged gas that glows with a faint blue color and stretches in an almost perfectly straight line. The other is the dust tail, made from tiny solid particles reflecting sunlight. It bends gently as different grains respond to gravity and sunlight in their own ways. But another surprise waits beneath all that brilliance. The nucleus itself ranks among the darkest known objects in the solar system, reflecting only about 4% of incoming sunlight. Its surface resembles black coal far more than fresh snow. Almost everything we admire from Earth comes from the expanding coma instead of the hidden nucleus. We also group comets by the time required to complete an orbit around the Sun. Those returning within 200 years usually arrive from the Kuiper Belt. Others spend thousands or even millions of years completing one circuit after leaving the distant Oort Cloud. Every return strips away another layer of ancient material. Little by little, each journey leaves a ribbon of dust scattered across space, while the comet itself grows smaller with every visit. Imagine drawing a boundary around everything the sun appears to rule. Then keep drawing. Continue far beyond every familiar planet, beyond the frozen frontier where ordinary maps usually end, until distance itself becomes difficult to picture. There, surrounding the entire solar system in every direction, lies a region so immense that no telescope has ever photographed it directly, yet its presence shapes nearly every long wandering comet we eventually witness. This immense reservoir is called the Oort Cloud, named after the Dutch astronomer Jan Oort, who proposed its existence in the year 1950 through careful mathematical study rather than direct observation. His calculations suggested that distant icy bodies must surround the solar system in a nearly spherical shell. Decades later, that conclusion remains one of astronomy's most remarkable deductions, built almost entirely from the paths traced by arriving comets. The inner edge of this cloud begins at roughly 2,000 astronomical units from the Sun, that is nearly 186 billion miles. One astronomical unit simply means the average distance between Earth and the Sun. The outer boundary may stretch to 100,000 astronomical units, which is about 9,300,000,000,000 miles, reaching almost halfway toward the nearest star beyond our own. Pluto, reached after 9.5 years by the spacecraft called New Horizons, circles at only about 40 astronomical units. The Oort cloud begins roughly 50 times farther away. Its population is almost beyond imagination. Current estimates suggest between 1 trillion and 2 trillion icy objects drift within this enormous sphere that may exceed the number of stars inside the Milky Way galaxy itself. Yet these frozen bodies remain almost completely hidden because each individual object is tiny, dark, and separated from its neighbors by astonishing distances. But how can we know such a place exists without seeing it? The answer comes from motion. Long period comets arrive from every direction imaginable. Some plunge inward from above the planetary plane, others rise from below it. Their orbits refuse to match the flat arrangement followed by the major planets, revealing a distant spherical source rather than a flattened disk. Most researchers believe these objects formed about 4.6 billion years ago during the birth of the solar system. They were scattered outward while the giant planets settled into their present orbits, preserving ancient ice, dust, and organic material in deep cold for billions of years. Their chemistry has remained largely unchanged throughout that immense span of time, but complete isolation never lasts forever. Passing stars, giant molecular clouds, and the gentle gravitational pull of the Milky Way galaxy itself slowly disturb the outer cloud. The galactic tide, meaning the combined gravitational influence of our galaxy, can gradually alter an orbit until one frozen traveler begins falling inward. That journey may require millions of years before reaching the warmth of the inner solar system. When you finally see one of these visitors, you are looking at material that has waited almost unchanged since the earliest chapter of our cosmic story. Far beyond Neptune, the solar system changes character once again. Instead of a distant spherical reservoir surrounding everything, we enter a broad, flattened region circling the sun like an immense frozen ring. This is the Kuiper Belt, a disk filled with ancient icy worlds that have remained on the outskirts of our planetary family since its earliest history. The Kuiper Belt begins near Neptune's orbit at about 30 astronomical units from the Sun, which is about 2,800,000,000 miles, and extends to roughly 50 astronomical units, that is nearly 4,650,000,000 miles. Within this enormous region drift hundreds of thousands of objects larger than 100 kilometers, which is about 62 miles, across. Countless smaller bodies accompany them, perhaps reaching into the trillions. Together they form an enduring population rather than a scattering of isolated objects. Pluto is the best known resident. For many years it seemed unique, almost like a lonely outpost beyond the planets. But improved observations revealed that Pluto belongs to a much larger community of frozen worlds, sharing similar sizes, compositions, and distant orbits. Its story changed because our understanding expanded, not because Pluto itself became different. Many short period comets begin their long inward migration here. Unlike visitors that require immense spans of time before returning, these comets complete an orbit around the Sun in fewer than 200 years. Neptune slowly alters their paths through repeated gravitational encounters spread across millions of years. Each encounter changes an orbit only slightly, yet together they guide icy bodies toward the inner solar system. But the Kuiper Belt has an even more restless neighborhood. Astronomers call it the scattered disk, a collection of objects following stretched and irregular paths. Their elongated orbits carry them much farther from the Sun before returning again. Many researchers consider this region the primary birthplace of the short period comets that eventually cross the planetary system. One remarkable member is Eris, discovered in the year 2005. It proved to be slightly larger than Pluto, forcing astronomers to reconsider what truly defines a planet. That debate ultimately led to Pluto's reclassification as a dwarf planet, reshaping textbooks while revealing how much remained to be learned about the solar system's distant frontier. But the Kuiper Belt also preserves evidence of an ancient upheaval. The NICE model, named after the French city where it was developed, proposes that Jupiter and Saturn gradually shifted their orbits during the solar system's youth. Those migrations disrupted countless frozen bodies, sending enormous numbers inward during the era known as the Late Heavy Bombardment, roughly between 4.1 and 3.8 billion years ago. Some scientists believe those impacts delivered much of Earth's water. Jupiter, then, assumed a complex role, sometimes redirecting incoming comets away from our world, while at other times capturing them into entirely new paths around the Sunday. Few objects have crossed the human story as faithfully as Halley's comet. Civilizations rose and disappeared beneath its returning arc, yet the comet continued its patient circuit around the Sunday. When you follow its history, you are tracing a single traveler through more than 2,300 years of human memory, connecting people who never knew one another but looked upward at the same celestial visitor. The earliest confirmed record comes from Chinese astronomers in the year 240 before the Common Era. Their careful observations became the first surviving description that can confidently be matched to Halley's comet. Centuries later, observers across Europe, the Middle East, and Asia recorded the same returning object without realizing they were witnessing one familiar body instead of many unrelated comets. Its journey around the Sun requires about 75 to 76 years. That rhythm is long enough for generations to pass, yet short enough that some people are fortunate enough to witness the comet twice during a lifetime. Every return adds another page to one of the longest continuous observation records in astronomy. One appearance became permanently woven into history. The Bayeux Tapestry, created during the 11th century, shows the comet blazing above anxious English nobles in the year 1066 during the Norman conquest. Many believed the glowing visitor foretold the defeat of King Harold. Across much of history, the comet carried meaning far beyond science. But understanding gradually replaced fear. The English astronomer Edmund Halley examined reports from the years 1531, 1607, and 1682. Using the laws of motion developed by Sir Isaac Newton, he concluded these were not separate objects at all. They represented one comet returning again and again. Halley boldly predicted it would reappear in the year 1758. He never witnessed that triumph. Edmund Halley died in the year 1742, 16 years before the prediction proved correct. When the comet returned on schedule, it transformed astronomy by demonstrating that these wandering objects followed predictable paths rather than mysterious impulses. Public fascination remained powerful. During the comet's return in the year 1910, newspapers reported that Earth would pass through its tail, which contained traces of the poisonous gas called cyanogen. Fear spread rapidly. Millions purchased gas masks and bottled air, expecting disaster. Nothing happened. The tail was so extraordinarily thin that our planet crossed it without any noticeable effect. But the return, during the year 1986, brought a different milestone. Although the viewing conditions from Earth disappointed many observers, the European Space Agency launched the spacecraft called Giotto to meet the comet directly, passing within 596 kilometers, which is about 370 miles, of the nucleus. Giotto captured humanity's first detailed images of a comet's heart. The nucleus appeared dark, irregular, and surprisingly shaped like a rough potato. Powerful jets of gas and dust burst from its surface, revealing that this familiar visitor remained active after thousands of years beneath human eyes. There are moments when exploration stops being a distant observation and becomes a meeting. That moment arrived on the 12th of November, 2014, when humanity accomplished something once considered almost impossible. After traveling about 6.4 billion kilometers, which is about 3.98 billion miles, across 10 years, a spacecraft finally reached a comet and attempted the first landing ever made upon one. The destination carried an equally remarkable name, Comet 67P Churyumov-Gerasimenko, honoring the two Soviet astronomers, Klim Churyumov and Svetlana Gerasimenko, who identified it from a photographic plate in the year 1969 at the Alma-Ata Observatory. By the time the spacecraft Rosetta arrived, during August of 2014, the comet had become one of the best studied small worlds in the solar system. Its appearance surprised nearly everyone. Rather than resembling a smooth, icy sphere, the nucleus looked like a giant rubber duck formed from two distinct lobes connected by a narrow neck. The entire object measured about 4.3 kilometers, which is about 2.7 miles, by 4.1 kilometers, that is nearly 2.5 miles. Rosetta remained beside it for more than 2 years, matching its motion as both traveled together around the Sunday. But the boldest part of the mission was still ahead. A small lander called Philae separated from Rosetta and drifted toward the surface. It weighed 100 kilograms and carried harpoons designed to anchor it immediately after touchdown. The harpoons never fired. Instead, the lander bounced once, then again, before finally coming to rest beneath towering terrain where sunlight rarely reached its solar panels. Even with those setbacks, Philae transmitted 64 hours of scientific observations before exhausting its available power. Those brief hours transformed our understanding of comets. Instead of a featureless frozen ball, the surface revealed immense cliffs, rising nearly 900 meters, which is about 2,953 feet, broad plains covered in fine material, deep sinkholes, enormous boulders, and patches of exposed ancient ice. Researchers uncovered another unexpected detail through instruments that sampled escaping gases. If you could somehow stand there without danger, the surrounding mixture would resemble the smell of rotten eggs, horse urine, bitter almonds, and formaldehyde. These scents reflected a complex blend of volatile compounds escaping from the warming nucleus. But perhaps the most significant discoveries came from chemistry. Measurements showed that the water released by this comet contained a different balance of ordinary hydrogen and the heavier form called deuterium than the water filling Earth's oceans. That difference suggested this family of comets probably supplied only a small portion of our planet's water. At the same time, Rosetta identified glycine, the simplest amino acid and one of the molecular building blocks used by living organisms. Finding such an organic molecule drifting within the comet's surrounding coma strengthened the idea that these ancient travelers carried ingredients capable of contributing to life's earliest chemistry across the young solar system. Look out across any ocean, and you are seeing one of Earth's greatest mysteries. Water covers about 71% of our planet, yet the young Earth formed in a region where conditions were believed to be too warm for lasting water ice to survive. The earliest building blocks were largely dry rock. Somewhere along the way, an extraordinary amount of water arrived. For many years, scientists narrowed the search to two leading suspects. One possibility pointed toward comets carrying frozen water inward from the distant reaches of the solar system. The other focused on a particular class of asteroids known as carbonaceous chondrites, ancient rocky bodies unusually rich in water and carbon containing compounds. Both appeared capable of delivering enormous quantities of material during the violent youth of the solar system. But how could we tell which source contributed more? Researchers turned to an invisible fingerprint hidden inside every drop of water. They measured the ratio between ordinary hydrogen and deuterium, a heavier form of hydrogen containing an additional particle within its nucleus. Different regions of the solar system formed with slightly different proportions of these two forms. That ratio preserves a record of origin, almost like a chemical birthplace written into the water itself. Earth's oceans contain a remarkably consistent deuterium ratio of about 1.56 multiplied by 10 to the negative fourth power. When astronomers examined long-period comets, such as Comet Hyakutake and Comet Hale-Bopp, they discovered significantly higher values, roughly twice the amount found in Earth's oceans. The difference was substantial enough to challenge the idea that these comets delivered most of our water. The Rosetta mission deepened that puzzle. Measurements taken from Comet 67P Churyumov-Gerasimenko showed that its water also possessed a mismatched deuterium ratio, even though it belonged to a completely different comet family. Many scientists responded by shifting their attention toward carbonaceous chondrite asteroids, whose water chemistry closely resembles that of Earth's oceans. But the story refused to settle into a simple answer. Observations made with the Herschel Space Observatory during the year 2011 revealed that Comet 103 P Hartley 2 carried water with a deuterium ratio strikingly similar to Earth's. Suddenly, at least one comet fit the expected pattern, suggesting the earlier picture had been incomplete. Today, The strongest explanation combines several sources rather than choosing only one. Water likely arrived through repeated deliveries from water rich asteroids, contributions from selected comets, and perhaps reserves already locked inside minerals as Earth itself assembled. You and I may be surrounded by an ocean created from many different journeys. Each wave carries a blended history gathered from countless travelers that crossed the young solar system before finding a permanent home on our world. Suppose every comet carried more than frozen water and ancient dust. Suppose each one also transported a collection of complex molecules assembled long before Earth became a living world. That possibility has gradually shifted from imaginative speculation toward a serious scientific question, driven by discoveries that continue to accumulate with every new mission and laboratory analysis. The amino acid called glycine, identified around Comet 67P Churyumov-Gerasimenko, was only one part of a much broader picture. Scientists have now detected more than 50 different organic molecules within comets, including increasingly complex carbon-based compounds. Organic molecules simply mean chemicals built around carbon, the element that forms the framework of every known living organism. They are not alive themselves, yet they provide essential ingredients for biology. Another important clue arrived through the Stardust mission of the National Aeronautics and Space Administration. During the year 2004, the spacecraft collected tiny particles from Comet Wild 2 and returned them safely to Earth. 5 years later, detailed laboratory studies confirmed the presence of glycine within those precious samples. Finding the same amino acid in different comets strengthened confidence that such chemistry is widespread rather than unusual. But some researchers have wondered whether comets carried more than ingredients alone. The idea called panspermia proposes that the seeds of life, or perhaps even dormant microscopic organisms, might travel through space inside comets and asteroids before reaching suitable worlds. In simple terms, panspermia suggests life could spread between planetary systems instead of beginning independently on every planet. During the 1970s and 1980s, the astronomers Fred Hoyle and Chandra Wickramasinghe argued that interstellar dust clouds might contain complex organic material and perhaps biological particles. Their proposals sparked intense debate. It remains controversial today, yet scientists continue testing aspects of the idea because observations keep revealing unexpected chemical richness throughout space. Timing also invites attention. Roughly 4 billion years ago, during the period known as the Late Heavy Bombardment, enormous amounts of cometary material struck the young Earth. The oldest evidence for life appears in the geological record soon afterward. That sequence does not prove a connection, but it encourages careful investigation. Comets also contain formaldehyde, hydrogen cyanide, and ammonia, chemicals capable of participating in reactions that produce amino acids under suitable conditions. Laboratory studies beginning with the famous Miller-Urey experiment demonstrated that such molecules can assemble naturally when supplied with energy. No living cells are required to begin that chemistry. The deeper implication remains both simple and profound. Comets may never have delivered living organisms to Earth, but they may have supplied the molecular toolkit from which biology eventually emerged. The origin of life remains one of science's greatest unanswered questions, and no single explanation has earned universal acceptance. Yet each newly studied comet strengthens the possibility that these ancient travelers helped prepare the stage long before the first living cell appeared. Picture the young inner solar system before familiar landscapes existed. Worlds had already formed, yet stability remained far away. Across hundreds of millions of years, countless icy and rocky bodies swept inward from the outer regions, striking planets with relentless force. Between roughly 4.1 billion and 3.8 billion years ago, this extraordinary era reshaped nearly every solid surface close to the Sunday. The clearest record survives on the Moon. Unlike Earth, the Moon has no moving tectonic plates, almost no erosion, and no widespread volcanic recycling to erase ancient scars. Its heavily cratered highlands preserve an almost uninterrupted history of that violent age. Every large basin records another immense collision, allowing us to reconstruct an episode that has largely vanished from our own planet. Earth shared the same dangerous neighborhood, but our world remained geologically active. Moving crust, flowing water, wind, and volcanism gradually erased nearly all direct evidence of those ancient impacts. The absence of visible craters does not mean they never existed. Instead, Earth's changing surface slowly buried nearly every trace beneath younger landscapes. Many planetary scientists connect this period to the Nice model, named after the French city where it was first developed. According to this explanation, Jupiter and Saturn eventually entered a gravitational resonance, meaning their orbital motions began reinforcing one another through repeated gravitational interactions. That change destabilized the outer solar system. Neptune and Uranus migrated outward, scattering enormous numbers of Kuiper Belt and Oort Cloud objects toward the inner planets. But the scale stretches far beyond ordinary imagination. Some estimates suggest the Moon alone absorbed impacts totaling more than 20,000 times the mass of the object responsible for the extinction of the non-avian dinosaurs. All of those collisions occurred within only a few 100 million years, transforming the appearance of every exposed surface. Earth endured repeated devastation. The largest impacts may have vaporized entire oceans, filling the atmosphere with superheated steam before water condensed once again. Crust fractured repeatedly. Fresh lava spread across enormous regions. Conditions that seem impossible for life today may have occurred several times during this remarkable chapter. Yet, an extraordinary puzzle follows. Geological evidence suggests that the earliest traces of life appeared surprisingly soon after the bombardment declined. Some researchers propose that simple organisms survived beneath the surface around deep hydrothermal vents, where hot mineral-rich water circulated through protected environments beyond the reach of the worst impacts. But another possibility remains equally compelling. Rather than merely surviving the bombardment, life's chemistry may have benefited from it. Every impact delivered fresh minerals, organic molecules, and enormous bursts of energy capable of driving complex chemical reactions. Those repeated encounters could have created ideal conditions for increasingly sophisticated molecular systems to emerge. When we examine this ancient era today, destruction and creation become difficult to separate. The late heavy bombardment stands as the most violent chapter in Earth's known history. It may also have prepared the world that eventually allowed you and me to exist. For the first time in recorded history, humanity did not simply imagine a planetary collision. We watched one unfold. During the month of July in the year 1994, telescopes around the world followed an extraordinary sequence of impacts as a comet crashed into Jupiter, transforming an abstract danger into an unforgettable reality. The visitor had already experienced a remarkable journey before the collision. Comet Shoemaker Levy 9 had wandered too close to Jupiter during an earlier pass and became trapped by the giant planet's immense gravity. As it swept near Jupiter once again, tidal forces, meaning differences in gravitational pull across the comet's length, stretched, and ultimately tore it apart. The nucleus fragmented into 21 separate pieces, forming a chain that extended roughly 1.1 million kilometers, which is about 684,000 miles. Astronomers quickly nicknamed the formation a string of pearls. The comet was discovered only 16 months before impact by Carolyn Shoemaker, Jean Shoemaker, and David Levy while examining photographic images taken at the Palomar Observatory. Instead of witnessing another routine comet, they had unknowingly found an object already committed to a spectacular fate. Between the 16th and the 22nd days of July, each fragment plunged into Jupiter's southern hemisphere. One after another, enormous explosions erupted beyond the planet's visible edge before rotating into view as Jupiter turned. Even modest backyard telescopes revealed fresh scars spreading across the cloud tops, allowing people everywhere to witness the aftermath with their own eyes. But one fragment stood above the rest. The piece identified by the letter G produced a fireball that climbed roughly 3,000 kilometers, which is about 1,864 miles above Jupiter's cloud layers. It also created a dark atmospheric stain, larger than Earth's entire diameter. That immense mark remained visible for months before gradually fading into the surrounding atmosphere. The energy released during the complete series of impacts reached an estimated 6 million megatons of trinitrotoluene, approximately 600 times greater than the explosive power of the entire global nuclear arsenal combined. Such numbers stretched almost beyond comprehension, yet Jupiter displayed them on a planetary scale. Scientists gained something invaluable from this event. For the first time, they observed a major comet impact as it happened, comparing real measurements against theoretical predictions. Models describing atmospheric shock waves, plume formation, and impact heating suddenly became grounded in direct evidence rather than mathematical expectation alone. But the consequences extended far beyond Jupiter itself. Planetary defense shifted from an interesting scientific discussion into an urgent, practical responsibility. Tracking programs, searching for hazardous asteroids and comets, received increased attention and stronger financial support after the collision demonstrated exactly what large impacts can do. Carolyn Shoemaker remained one of the defining figures of that effort. Working patiently with a stereo microscope to compare photographic plates by hand, she discovered 32 comets during her remarkable career, more than any other individual. Her careful observations helped reveal one of the most dramatic events ever witnessed in the history of planetary science. Long after we began tracing the graceful paths of comets across the sky, another realization slowly emerged. Beauty and danger can share the same orbit. Every object circling the sun carries energy, and when one crosses Earth's path, that stored motion can be released in an instant beyond anything our civilization has ever produced. The object that struck Earth roughly 66 million years ago and ended the age of the Nonavian dinosaurs was almost certainly an asteroid. Yet when a massive body collides with a planet, the distinction between asteroid and comet becomes less important than its speed, mass, and direction. Both are ancient remnants of solar system formation. Both become devastating when gravity guides them toward a world. But comets possess one characteristic that makes them especially alarming. They travel much faster. A typical asteroid may strike at around 20 kilometers per second, which is about 12.4 miles per second. Some comets can arrive at speeds approaching 70 kilometers per second, that is nearly 43.5 miles per second. Kinetic energy is the energy carried by motion, and it rises dramatically as velocity increases. Even a comet, comparable in size to an asteroid, could release far greater destructive power simply because it arrives so much faster. A striking reminder came during the morning of June 30th, 1908, above the forests of Siberia. An object estimated to measure between 50 and 80 meters across, that is nearly 164 to 262 feet, exploded high in the atmosphere before reaching the ground. The blast released energy comparable to roughly 10 to 15 megatons of trinitrotoluene, flattening about 2,150 square kilometers, which is about 1,336 square miles of forest. No impact crater remained because the object completely disintegrated before striking Earth's surface. Today, researchers believe the Tunguska object was most likely a stony asteroid rather than a comet. Even so, the event demonstrated beyond doubt that relatively modest objects from space can produce destruction across an area comparable to that of a major city and its surrounding landscape. But long-period comets introduce an additional challenge. They approach from the distant reaches of the solar system on enormous elongated paths that often provide very little warning. Asteroids that threaten Earth can sometimes be tracked years before a possible encounter. A newly discovered long-period comet might allow only months to prepare. Would that ever be enough? Comet Swift-Tuttle illustrates both the danger and the uncertainty. It is the parent body of the annual Perseid meteor shower and measures roughly 26 kilometers across, which is about 16.2 miles. That makes it more than twice the width of the object, linked to the extinction of the no-Navian dinosaurs. Current orbital calculations show no threat of impact for at least the next 2,000 years, although predictions become less certain over extremely long timescales. Humanity has already demonstrated that an asteroid's course can be altered through a carefully planned spacecraft collision. But comets present a very different problem. They are often larger, considerably faster, and discovered much later. Our ability to change their path remains an ambition rather than a completed achievement. Some of the oldest visitors to our skies arrive without anyone noticing the traveler that left them behind. As Earth continues its yearly path around the Sun, we repeatedly cross invisible streams of dust scattered long ago by passing comets. The comet itself may be far beyond the planets or still making its slow journey around the Sun, yet the trail remains, stretching along its entire orbit for thousands of years. Each crossing gives you one of the most familiar sights in the night sky. The Perseid meteor shower arrives every year during the month of August. Under favorable conditions, you may see as many as 100 meteors each hour. Every bright streak belongs to debris released by Comet Swift-Tuttle, whose most recent passage through the inner solar system occurred during 1992. Although the comet has long since continued onward, countless tiny particles still occupy its ancient path, waiting for Earth to pass through them once again. But another display can become even more astonishing. The Leonid meteor shower, appearing each November, comes from Comet Tempel-Tuttle. Roughly every 33 years, Earth encounters a particularly dense part of the debris stream. During these rare encounters, ordinary meteor activity transforms into a true meteor storm. The famous display of 1833 was so overwhelming that observers described the heavens as raining fire. Modern estimates suggest nearly 100,000 meteors flashed across the sky every hour, turning darkness into continuous motion. The Geminid meteor shower, arriving each December, presents an unexpected twist. Its parent body is not considered a traditional comet at all. Instead, it is the asteroid known as 3,200 Phaethon. Yet this unusual object sheds material whenever it swings close to the sun, behaving in ways remarkably similar to a comet. The distinction between rocky asteroids and icy comets becomes less certain when nature refuses to follow our categories. You also encounter the path of Halley's comet twice every year. During the month of May, its debris creates the Eta Aquariid meteor shower. During the month of October, another crossing produces the Orionid meteor shower. One ancient comet leaves two annual reminders of its continuing journey, even while the nucleus itself remains far beyond our view. But what you call a shooting star is almost never a fragment of a comet's solid nucleus. Most meteoroids are no larger than grains of sand. They plunge into Earth's atmosphere between roughly 100 kilometers, which is about 62 miles, and 200 kilometers, which is about 124 miles, above the surface. An even stranger detail follows. The particle does not ignite simply by rubbing against the air. Instead, it compresses the air in front of it with tremendous force. That compressed air becomes intensely hot, often exceeding 1,600 degrees Celsius or 2,912 degrees Fahrenheit. The glowing air and the rapidly vaporizing particle together create the brilliant streak that lasts only a heartbeat, marking the place where Earth briefly crossed the forgotten footsteps of a comet. Sometimes the greatest discovery is recognized only after it is already leaving. During the month of October in the year 2017, astronomers studying fresh observations from the Panoramic Survey Telescope and Rapid Response System in Hawaii noticed a faint object crossing the solar system along an impossible path. Its trajectory was unmistakably hyperbolic, meaning it was not bound to the Sunday. It had entered from interstellar space and would never return. The object received the formal designation 1I 2017 U1 before being given the Hawaiian name Oumuamua, meaning scout or messenger arriving first from afar. For the first time in recorded history, humanity had confirmed the passage of an object born around another star. You were looking at material that had spent untold ages traveling through the immense darkness between stellar systems before briefly crossing our cosmic neighborhood. But almost everything about it challenged expectations. As astronomers measured changes in its brightness, known as a light curve, they inferred an astonishing shape. Oumuamua appeared to be roughly 10 times longer than it was wide. Some researchers favored an elongated, cigar-like body. Others suggested an extremely thin, flattened disk. Neither possibility resembled the familiar asteroids and comets cataloged throughout our own solar system. Its speed deepened the mystery. Oumuamua raced past the Sun at about 87.7 kilometers per second, which is about 54.5 miles per second. Nothing moving that quickly could have originated from the family of objects orbiting our own star. It belonged somewhere else, long before the Sun ever captured a glimpse of it. Then came the greatest surprise. As Oumuamua departed, astronomers measured a slight additional acceleration that gravity alone could not explain. A comet often behaves this way because warming ice produces jets of escaping gas. Those natural thrusters gently push the nucleus, altering its motion. Yet telescopes detected no glowing coma, no tail, and none of the familiar signs expected from an active comet. But without those clues, explanations became far more speculative. Harvard astronomer Avi Loeb proposed that Oumuamua might even be an artificial light sail, a thin structure propelled by the pressure of starlight and perhaps created by another civilization. Most researchers rejected that interpretation, favoring natural origins instead. Even so, no single explanation accounted for every observation without leaving unanswered questions. One leading idea suggests that Oumuamua was a fragment chipped from a distant world resembling Pluto, rich in exotic hydrogen ice that could evaporate without producing the familiar appearance of an ordinary comet. Other researchers have explored different combinations of unusual ices, porous structures, or rare geological histories. None has gained universal acceptance. By the time astronomers recognized how extraordinary this visitor truly was, it had already slipped beyond any practical reach. No spacecraft could be redirected quickly enough to intercept it. We gathered only a brief collection of observations before it disappeared forever into interstellar space, carrying its deepest secrets onward between the stars, leaving us with one fleeting encounter and a reminder that our solar system is not isolated from the wider galaxy. The next messenger from another star arrived with far fewer mysteries, yet its story proved equally remarkable. During the month of August, in the year 2019, amateur astronomer Gennady Borisov was scanning the sky with a telescope he had largely built himself in Crimea. Among countless familiar points of light, he noticed one object moving in a way that immediately deserved closer attention. Within days, astronomers confirmed that it had not originated within our own solar system. The object received the designation 2I Borisov. Unlike the previous interstellar visitor, this newcomer behaved exactly as astronomers expected a comet to behave. It possessed a glowing coma surrounding its nucleus. A luminous tail stretched away from the sunday. As sunlight warmed its icy surface, gases escaped into space through outgassing, the natural release of vapor that forms a comet's temporary atmosphere and sweeping tail. Its path through the solar system told the rest of the story. Borisov followed a hyperbolic orbit, meaning it was passing through only once before continuing toward interstellar space. This was the first confirmed interstellar comet ever observed, giving scientists an opportunity they had hoped for after the fleeting passage of the earlier visitor. Although its solid nucleus measured only about 1/2 kilometer across, which is about 0.31 miles, the surrounding coma expanded dramatically as it approached the sunday. During its closest passage, that glowing cloud reached roughly 100,000 kilometers in diameter, which is about 62,137 miles. A tiny frozen body had surrounded itself with an atmosphere vastly larger than many planets. But its greatest contribution came from its chemistry. Powerful observatories, including the Hubble Space Telescope, detected familiar ingredients within the escaping gases. Water was present. Carbon monoxide appeared as well. Carbon dioxide emerged alongside them. Their relative abundances broadly resembled those measured in many comets formed around our own sunday. That resemblance carried profound meaning. If another planetary system assembled comets from nearly the same ingredients, then the chemistry that shaped our own solar system may not be unusual at all. Water, carbon compounds, and complex organic molecules could be common products wherever stars and planets are born. You begin to see our neighborhood less as an exception and more as one example within a much larger pattern. But Borisov also revealed something unexpected about the population of interstellar visitors themselves. Its discovery suggested these travelers may pass through our solar system far more often than anyone previously believed. For generations, they simply escaped detection because telescopes lacked the sensitivity and wide fields of view needed to find such faint, fast-moving objects. Statistical studies following Borisov's passage indicate that several interstellar objects larger than 1 kilometer which is about 0.62 miles, may be inside our solar system at any given time without being noticed. As new observatories become more capable, including the Vera C. Rubin Observatory, astronomers expect to discover dozens of these wandering visitors every year, transforming rare curiosities into an entirely new field of exploration. Long before any spacecraft reached these frozen wanderers, each comet had already been preserving a chemical record of astonishing depth. As we examine them more closely, you begin to see something unexpected. A comet is less like a dirty snowball and more like a traveling laboratory, carrying an inventory assembled before the planets themselves had fully taken shape. Water is the dominant volatile, meaning a substance that readily changes from solid ice into gas when warmed by sunlight. In a typical comet, water accounts for roughly 80% of the escaping gases by volume. But that familiar ingredient is only the beginning. Carbon monoxide and carbon dioxide usually follow as the second and third most abundant volatile materials, although some distant comets tell a different story. Those that never approach the sun more closely than Jupiter remain so cold that water stays largely frozen beneath the surface. Carbon monoxide escapes more readily under those conditions, allowing it to become the dominant gas instead. Every orbit writes a different chemical signature. Every comet preserves its own history. As increasingly sensitive instruments examine these visitors, the list of detected molecules continued to grow. Methanol appeared, formaldehyde followed. Scientists also identified methane, ethane, acetylene, and hydrogen cyanide through infrared and radio spectroscopy, techniques that reveal chemical identities by measuring the unique wavelengths of light absorbed or emitted by each molecule. Together, these compounds demonstrated that cometary chemistry extends far beyond frozen water alone. But one discovery carried particular weight. The Rosetta mission detected phosphorus within the material released from Comet 67P. Phosphorus is one of the 6 essential chemical elements required by every known living organism. It helps build genetic material, cell membranes, and the molecules that store and transfer energy inside living cells. Finding it inside a comet strengthened the possibility that these travelers supplied important ingredients to the young Earth long before biology emerged. The surprises continued. Scientists identified complex organic compounds, including ethylene glycol, a simple sugar alcohol, along with glycoaldehyde, the simplest known sugar. Molecules such as these are directly relevant to the chemistry that can eventually produce ribonucleic acid, one of the fundamental molecules used by living systems to store and process genetic information. But perhaps the oldest treasures lie hidden even deeper. The isotopic ratios locked inside cometary ice, meaning the relative abundance of different forms of the same element, preserve the physical conditions that existed when the solar nebula first condensed about 4.6 billion years ago. Mixed among those frozen layers are presolar grains, microscopic particles forged inside ancient stars that lived and died billions of years before our sun was born. Protected inside cometary ice through the entire history of the solar system, they allow you to hold, in scientific terms, material older than the sun itself. Imagine looking upward one evening and finding a new light stretching across the heavens, brighter than familiar stars and growing longer with each passing night. For most of human history, such an appearance inspired wonder as readily as fear. Without modern astronomy, a great comet seemed to arrive without warning, blazing across the sky like a message written for the entire world. Among the earliest of these remarkable visitors was the Great Comet of 1680, later known as Kirch's Comet. German astronomer Gottfried Kirch first detected it through a telescope during November of 1680, making it the first comet discovered with that instrument rather than by the unaided eye. As it approached the sun, it brightened until people could see it even in broad daylight. Its magnificent tail stretched roughly 70 degrees across the sky, more than one-third of the entire celestial dome visible above you. But its greatest influence reached far beyond spectacle. Sir Isaac Newton examined observations of the comet's motion while refining his theory of universal gravitation, the idea that every object with mass attracts every other object. By successfully calculating the comet's orbit, he demonstrated that the same mathematical laws governing an apple falling toward Earth also controlled wandering bodies moving through the solar system. The heavens had become measurable. More than a century later, another visitor lingered with remarkable patience. The Great Comet of 1811 remained visible to the unaided eye for approximately 260 days, the longest recorded naked eye appearance of any comet in history. Across Europe, people attached their own meanings to its presence. Napoleon Bonaparte reportedly viewed it as a favorable sign before beginning his invasion of Russia. Meanwhile, vineyards in France produced an exceptional harvest, and that celebrated vintage became known as Comet wine, a name remembered by wine historians even today. Centuries passed, yet the power of a brilliant comet never faded. Comet Hale-Bopp became one of the most closely observed comets ever recorded after its discovery during the 1990s. Visible without optical aid for about 18 months, it possessed a nucleus estimated at 60 kilometers, which is about 37 miles, across, making it one of the largest known comets observed from Earth. Even city lights failed to hide its brilliance. But fascination also took a tragic turn when members of the Heaven's Gate group wrongly believed a spacecraft accompanied the comet, leading to the deaths of 39 people during March of 1997. Another astonishing traveler appeared with almost no warning. Comet Lovejoy was discovered only 6 days before racing through the Sun's outer atmosphere, passing within roughly 140,000 kilometers, which is about 87,000 miles, of the solar surface. Many expected complete destruction, but it endured the intense encounter, emerging on the far side with a dramatically reshaped tail, reminding us that comets can still surprise you, even after centuries of careful observation. There are moments when a comet chooses the most dangerous path imaginable, turning inward until it races toward the blazing edge of the sun itself. From our distant viewpoint, the journey seems impossible. Yet these remarkable travelers repeat it again and again, following ancient orbits carved long before human civilization began watching the sky. These are known as sun-grazing comets, meaning their paths carry them within only a few solar radii of the sun's visible surface. At such distances, the environment becomes extraordinarily hostile. Most never survive. Intense heat vaporizes their frozen material, while the sun's enormous gravity stretches them through tidal forces, the unequal pull of gravity across the comet's body that can tear fragile objects apart. But many of these visitors belong to a much larger family. The Kreutz sungrazers are believed to be fragments of one immense comet that shattered during repeated close encounters with the Sunday. Astronomers suspect that the Great Comet of 1106 was itself one of those fragments, while that spectacular object may also have descended from an even older parent that broke apart centuries earlier. Every surviving piece continues tracing nearly the same perilous route, preserving a family history written across generations of comets. Thousands have now been identified. Most escape notice until the Solar and Heliospheric Observatory began operating during the 1990s. Although designed primarily to study the Sun, it became the most successful comet discovery instrument ever built. More than 4,000 comets have been found through its observations, the overwhelming majority belonging to the Kreutz family. Nearly all are small enough to evaporate completely before reaching their closest approach. As one of these fragments plunges inward, its speed becomes astonishing. A typical Kreutz sungrazer can exceed 500 kilometers per second, which is about 311 miles per second. That equals roughly 17 hundredths of 1% of the speed of light. At the same time, the nucleus may reach temperatures exceeding 2000 degrees Celsius or 3632 degrees Fahrenheit, hot enough to melt iron. But every rule has an exception. Comet Lovejoy swept through the Sun's outer atmosphere at roughly 500 kilometers per second, which is about 311 miles per second, while surrounded by plasma approaching 1 million degrees Celsius or 1,800,000 degrees Fahrenheit. Plasma is a state of matter in which atoms have been stripped of many of their electrons, creating an intensely energetic gas. Against every expectation, Lovejoy emerged alive. Its rapidly evaporating outer layers briefly shielded the frozen interior, buying precious moments before complete destruction could occur. When it reappeared, its original tail had vanished, and a completely new one began forming almost immediately. Scientists watching the event described images unlike anything previously recorded. But the greatest surprise remained where the comet had traveled. Even only 140,000 kilometers, which is about 87,000 miles, above the visible surface, it moved through the Sun's corona, the Sun's vast outer atmosphere, where million-degree plasma is spread so thinly that it exerts remarkably little physical pressure despite its extraordinary temperature. Nothing in the solar system travels forever unchanged. Even the most brilliant comet is living through a gradual ending, losing tiny pieces of itself every time it returns from the darkness toward the warmth of the Sunday. Each passage strips away another layer, leaving behind a smaller and older traveler than the one that arrived before. A comet survives by sacrificing itself. As sunlight warms its surface, frozen gases transform directly into vapor, carrying dust and rocky grains into space. This process, called sublimation, is the direct change of ice into gas without becoming liquid first. The beautiful tails we admire exist because the nucleus is steadily disappearing. Every glowing display is also an act of erosion. Halley's comet provides one of the clearest examples. During each orbit around the Sun, it loses approximately 6 meters of surface material, which is about 20 feet. At that pace, astronomers estimate it will become almost unrecognizable after roughly 2,300 additional journeys around the Sunday. That sounds immense on a human timescale, yet it represents only a brief chapter in the life of the solar system. But some comets never reach such an orderly conclusion. They simply fall apart. During the year 2000, the Hubble Space Telescope watched Comet Linear, officially designated Comet Linear, capital letter C, slash 1999, capital letter S, 4, disintegrate completely. Instead of remaining a single body, it dissolved into countless smaller fragments before fading into a diffuse cloud that gradually dispersed into space. Scientists believe such collapses can result from rotational stress, uneven forces created by escaping gases, or the gradual weakening of the comet's fragile interior. Others meet an even more dramatic fate. A close encounter with a massive planet can produce tidal disruption, meaning gravity pulls much more strongly on one side of the comet than the other until the entire body tears apart. We have already seen this happen near Jupiter, where a single comet became a chain of separate fragments before continuing its final journey. Yet, destruction is not the only ending. Some comets simply grow old. After repeated passages near the Sun, they exhaust most of their easily vaporized material while leaving behind a dark, rocky core. These dormant or extinct comets continue circling the Sun without producing a visible coma or tail, making them almost impossible to distinguish from ordinary asteroids. That blurred boundary has already changed how we classify objects. The body, known as 2060 Chiron, was first cataloged as an asteroid after its discovery during 1977. But observations during 1988 revealed a developing coma, earning it recognition as both an asteroid and a comet. Another example: 3200 Phaethon sheds material despite its asteroid appearance, creating the Geminid meteor shower and becoming the first recognized rock comet. But the story continues as the Japan Aerospace Exploration Agency plans the Destiny Plus mission to fly past Phaethon and examine this remarkable transition in unprecedented detail. Long before computers searched the heavens without rest, every new comet depended upon patient human eyes. Night after night, observers stood beneath the stars, guiding binoculars or modest telescopes across familiar constellations, hoping that one faint blur would refuse to match any known object. Most evenings ended exactly as the previous ones had. Still, they returned. You can almost measure discovery in hours instead of distance. David Levy, who later helped discover Comet Shoemaker-Levy 9, devoted approximately 928 hours to methodically sweeping the sky before finding his first comet. That achievement represented years of persistence rather than a single fortunate evening. Every unsuccessful search refined his memory of the heavens until even the smallest unexpected glow became impossible to overlook. This tradition shaped the names that still appear across astronomy: Halley, Hale-Bopp, Lovejoy, Churyumov-Gerasimenko. Each reminds us that discovering a comet once depended primarily upon individual dedication rather than automated technology. A person's name became permanently attached to an object that would continue circling the Sun long after its discoverer had passed from history. But remarkable discoveries continued even as technology advanced. Australian amateur astronomer Terry Lovejoy found 5 comets between the years 2007 and 2015 using commercially available equipment from his suburban backyard. Among them was the spectacular sun-grazing Comet Lovejoy, officially designated Comet, capital letter C, slash 2011, capital letter W, 3, whose extraordinary journey near the Sun astonished astronomers around the world. His success demonstrated that careful observation still had a place beside increasingly sophisticated surveys. Even so, the balance gradually shifted. Around the middle of the first decade of the 21st century, automated observatories became the dominant comet hunters. Vast survey systems repeatedly photographed enormous areas of the sky every few nights, comparing fresh images against previous ones with specialized computer algorithms. Instead of relying upon human memory alone, these systems instantly highlighted tiny points of light drifting against the background stars. Among the most productive is the Panoramic Survey Telescope and Rapid Response System in Hawaii. Operating almost continuously, it detects objects so faint that no individual observer could realistically discover them through ordinary visual searching. Its sensitive cameras have transformed comet discovery from an occasional triumph into a steady scientific process, revealing visitors that earlier generations never had the ability to see. But the search is becoming even deeper. The Vera C. Rubin Observatory now conducts the Legacy Survey of Space and Time, repeatedly imaging the southern sky every 3 to 4 nights. Its extraordinary sensitivity reaches objects approximately 10 times fainter than those routinely detected by the Panoramic Survey Telescope and Rapid Response System. Astronomers expect it to discover hundreds of new comets each year and, over its planned decade of operation, perhaps thousands of interstellar visitors that briefly cross our shared celestial neighborhood before continuing into the vast darkness between the stars. There comes a moment when distant points of light stop being enough. We begin building machines that can cross the emptiness on our behalf, carrying our questions far beyond Earth until they arrive beside worlds no human could ever reach. Each Comet mission has expanded that conversation, revealing details no telescope alone could have uncovered. The first close encounter came in the year 1986 when the European Space Agency launched the Giotto spacecraft toward Halley's Comet, passing within 596 kilometers, which is about 370 miles, of the nucleus. Giotto survived a violent collision with a fast-moving dust particle that briefly knocked it off course. Even after that impact, it returned humanity's first close images of a cometary nucleus. The surface appeared almost black, irregular in shape, and punctuated by isolated regions where powerful jets of gas erupted into space. But one encounter could never tell the whole story. In the year 2001, the National Aeronautics and Space Administration sent Deep Space One past Comet Borrelly. Its cameras revealed a nucleus resembling a bowling pin, marked by smooth plains, rough cliffs, and energetic dust jets. The similarities to Halley's Comet suggested these active regions were common features rather than unusual exceptions. The journey became even more personal with the Stardust mission. Flying through the glowing coma of Comet Wild 2 in the year 2004, the spacecraft captured microscopic particles inside an extraordinarily light material called aerogel, a substance so porous that fast-moving grains could be collected without shattering. Those precious samples returned to Earth in the year 2006, becoming the first physical comet material ever recovered. Scientists identified crystalline silicates along with the amino acid glycine, a molecule used by living organisms to build proteins. But another mission chose a far more dramatic experiment. Deep Impact released a copper impactor weighing 370 kilograms, which is about 816 pounds, directly into Comet Temple, one at a speed of 10.2 kilometers per second, which is about 6.3 miles per second. The enormous plume concealed the newly formed crater from the observing spacecraft. Analysis later showed unexpectedly fine material and less ice than researchers had anticipated beneath the surface. The most complete portrait arrived with Rosetta and its companion lander, Philae. For more than 2 years, the European Space Agency spacecraft orbited Comet 67, Churyumov-Gerasimenko, while Philae attempted the first landing on a cometary nucleus. Together they catalogued organic molecules, mapped the nucleus in remarkable detail, and measured the changing chemistry of both the surface and surrounding coma as the comet approached the Sunday. Even missions with different destinations continue adding to this story. After its historic encounter with Pluto in the year 2015, the New Horizons spacecraft traveled onward through the Kuiper Belt, observing ancient icy bodies that supply many short-period comets. By studying their untouched surfaces, we glimpse the distant origins of countless future visitors before they ever begin their long fall toward the warmth of the inner solar system. Long before anyone understood where comets came from, people searched instead for what they meant. Across continents, separated by oceans and centuries, unfamiliar streaks of light inspired remarkably similar reactions. They were rarely welcomed. They were watched with anxious attention, woven into stories that tried to explain why the familiar sky had suddenly changed. Among the most careful observers were the astronomers of ancient China. Their records remain some of the finest surviving documents from the ancient world. The Mawangdui silk texts, dating to approximately 300 years before the birth of Jesus Christ, preserve illustrations of 29 distinct comet forms. Each appearance carried its own interpretation, linking differences in shape and brightness to predictions of war, famine, political upheaval, or the fortunes of rulers. For generations, careful observation and cultural belief developed side by side. But China was far from alone. In ancient Babylonia, astronomers referred to comets as the hairy star and recorded their appearances on clay tablets written in cuneiform, a system of wedge-shaped writing pressed into soft clay. These observations became part of extensive collections of omens. When unusual celestial events appeared, scribes compared them with earlier records, searching for patterns connecting the heavens to the rise and fall of kingdoms. The Roman world carried similar convictions into imperial history. After the assassination of Julius Caesar in the year 44 before the birth of Jesus Christ, a bright comet appeared during public games held in his honor. Many citizens believed they were witnessing Caesar's soul ascending among the gods. Augustus Caesar embraced that interpretation, placing the so-called Julian star into coins, monuments, and political imagery to strengthen both his own authority and the divine legacy of his adopted father. Across the Atlantic, indigenous civilizations developed traditions entirely independent of Europe or Asia. The Aztec people described comets as smoking stars and often associated them with the powerful figure Quetzalcoatl. Some historians have proposed that the arrival of Hernán Cortés in the year 1519, occurring near expectations surrounding Quetzalcoatl's return and possibly alongside the appearance of a comet, influenced the earliest responses to the Spanish expedition. The historical details remain debated, yet the connection illustrates how deeply celestial events could shape human decisions. But one careful observer helped transform those ancient interpretations forever. In the year 1577, the Danish astronomer Tycho Brahe measured the Great Comet using parallax, a method that determines distance by comparing an object's apparent position from different locations. His calculations showed the comet lay far beyond the moon rather than inside Earth's atmosphere. That single result challenged the long-accepted teachings of Aristotle and demonstrated that comets belonged to the wider cosmos. We still inherit stories born from wonder and uncertainty, yet you can also trace the beginning of modern astronomy to the moment careful measurement finally replaced inherited belief. For generations, the sky appeared neatly organized, each wandering object assigned a clear identity. A comet wore a glowing tail and arrived from the frozen outskirts of the solar system. An asteroid remained dark, rocky, and confined mainly to the broad belt between Mars and Jupiter. The categories felt permanent. They filled textbooks, guided observations, and shaped the way we imagined our celestial neighborhood. But nature rarely respects the boundaries we create. As telescopes grew more capable, Astronomers encountered objects that refused to remain inside familiar definitions. Some traveled along unmistakable asteroid paths, yet unexpectedly released dust into space. Others looked dormant for decades before awakening with delicate Comet, the diffuse clouds of gas and dust that surround active comet nuclei. The line dividing these families gradually became less convincing. One remarkable example arrived with the discovery of 133 P/Elst Pizarro, first identified during the year 1979 as an ordinary asteroid. It surprised observers during the year 1996 by developing a visible dust tail. Continued observations revealed repeated episodes of activity rather than a single collision. It became the first recognized member of what astronomers now call the main belt comets, objects occupying ordinary asteroid orbits while behaving like comets when buried ice becomes exposed. That discovery carried an important implication. Impacts from smaller bodies appear capable of uncovering pockets of ancient ice hidden beneath rocky surfaces. Once exposed to sunlight, that ice gradually changes directly from solid into gas, a process called sublimation, meaning a frozen substance becomes vapor without first melting into liquid. The escaping gas lifts fine dust into space, creating the familiar appearance once thought unique to distant comets. Water ice, it seemed, had been hiding much closer to home than expected. But the surprises continued beyond the asteroid belt. Between Jupiter and Neptune drifts a population known as the Centaurs, named after the mythical beings that combined human and horse. These objects also combine characteristics once considered incompatible. They follow unstable orbits, and many eventually migrate inward. As they approach greater warmth, some awaken and develop expansive comae, revealing that they were dormant comets waiting for favorable conditions. Chiron became the first known centaur after its discovery during the year 1977. Even while remaining beyond Saturn's orbit, it produced a coma where sunlight alone seemed too weak for ordinary water ice to sublimate efficiently. Researchers concluded that more volatile materials, including carbon monoxide and nitrogen, were likely escaping instead, demonstrating that different frozen compounds can awaken activity at very different distances from the sunday. We are left with a gentler picture of our solar system. Instead of isolated categories, you and we find a continuous spectrum stretching from rocky bodies to icy wanderers. More than 30 active asteroids have now been identified, and every new discovery softens another once certain boundary. The objects themselves have not changed. Only our understanding has. Long after a comet has slipped beyond easy view, it continues leaving something behind. Every journey around the sun releases countless tiny particles that drift away instead of returning to the nucleus. Over immense spans of time, these fragments spread throughout the solar system, building a vast veil known as the interplanetary dust cloud, sometimes called the zodiacal cloud. We move through this enormous structure every day, even though you rarely notice it. Under exceptionally dark skies, however, the cloud reveals itself. Before dawn or after dusk, a soft pyramid of light may rise along the path, followed by the planets. This phenomenon is called the zodiacal light, meaning sunlight scattered by countless microscopic dust grains suspended between the worlds. In places almost untouched by artificial illumination, its glow becomes strong enough to cast faint shadows across the landscape. The light seems delicate, yet it comes from an astonishing abundance of particles. But the cloud is never complete. Gravity, sunlight, and countless collisions steadily remove dust from the inner solar system. Fresh material must constantly replace what disappears. Current estimates suggest that comets contribute about 30,000 tons of dust every year, maintaining this broad haze across planetary space. Without that continuous supply, much of the cloud would gradually fade over thousands of years. Earth receives part of this ongoing delivery. Roughly 40,000 tons of extraterrestrial material settle onto our world each year, arriving as microscopic grains from both comets and asteroids. Mixed among them are presolar grains, tiny mineral fragments forged before the sun itself existed, along with chondrules, small rounded particles formed during the earliest stages of planetary construction. Complex organic molecules also accompany this steady descent, each grain carrying another fragment of an ancient story. Scientists have collected many of these particles using high-altitude aircraft flying through the stratosphere. The recovered interplanetary dust particles differ noticeably depending on their origin. Those believed to come from comets are often porous, fragile, and especially rich in carbon-containing compounds. Asteroidal particles generally appear denser and more compact. Even under a microscope, their different histories remain written into their structures. But the importance of cometary dust may reach beyond classification alone. Some researchers propose that this gentle rain of microscopic material continuously enriched the young Earth with complex organic compounds across billions of years. Instead of depending entirely upon rare, catastrophic impacts, our planet may have received a persistent supply, delivered grain by grain, season after season. While the earliest environments capable of supporting chemistry slowly evolved, the National Aeronautics and Space Administration mission called Stardust strengthened that possibility. Samples returned from Comet Wild. Two contained crystalline olivine and pyroxene, minerals requiring intense heat to form near the young Sunday. Their presence inside a distant comet revealed that material traveled enormous distances before becoming trapped in icy bodies. We discover that even the smallest speck of comet dust preserves evidence that the newborn solar system mixed itself far more thoroughly than anyone once imagined. Standing far beyond the rocky planets, Jupiter shapes the journeys of countless wandering objects without ever touching them. Its immense gravity reaches across enormous distances, subtly redirecting paths that have remained unchanged for millions of years. With more mass than all the other planets combined, Jupiter has become one of the principal architects of comet motion throughout the solar system. We cannot understand these icy travelers without also following the influence of this giant world. For many years, astronomers embraced an appealing idea known as the Jupiter Shield hypothesis. Proposed during the 1990s, it suggested that Jupiter intercepted or deflected most incoming long-period comets before they could threaten the inner solar system. Computer studies from that era even indicated that, without Jupiter, Earth might experience roughly 10,000 times more comet impacts. The giant planet seemed to stand as a faithful guardian, protecting the worlds closer to the Sunday. That conclusion reached beyond our own planetary neighborhood. It became part of the broader rare Earth argument, the proposal that planets capable of supporting complex life may require a massive outer companion to reduce catastrophic impacts. If Jupiter truly served as an effective shield, then worlds resembling Earth could be far less common throughout the galaxy than many had imagined. But improved computer simulations gradually revealed a more complicated picture. Jupiter certainly throws some incoming comets away from the inner solar system, sending them back into deep space or altering their paths beyond recognition. Yet the same powerful gravity can also redirect distant objects inward, placing them onto new trajectories that eventually cross the orbits of the terrestrial planets. The same force that removes danger can sometimes create fresh opportunities for encounters. Studies led by researchers including Kevin Grazier explored these competing effects in greater detail. Their calculations suggested that Jupiter may increase the number of short period comets entering the inner solar system, functioning at times more like a comet pump than an unchanging shield. A short period comet simply means one that completes repeated journeys around the Sun in less than about 200 years, allowing Jupiter many opportunities to reshape its orbit. Today, the scientific view has become more restrained. Jupiter is neither the flawless defender once celebrated, nor a persistent source of danger. Its overall influence on Earth's long-term impact rate appears relatively modest, with protective and disruptive effects balancing one another more closely than earlier models predicted. Reality proves richer than the simple stories we first tell ourselves. One remarkable example remains impossible to overlook. Comet Shoemaker Levy 9 had already been captured into orbit around Jupiter for decades before the giant planet's gravity tore it apart through tidal forces. The stretching effect created when gravity pulls more strongly on one side of an object than the other. The fragments later plunged into Jupiter itself. Other members of the Jupiter family of comets may also be temporary visitors, destined one day either to escape the planet's influence or to meet a similarly dramatic end. Every successful mission has answered questions that once seemed impossible, yet each close encounter has also uncovered new mysteries waiting beneath the surface. After decades of exploration, we know far more about comets than any generation before us. But you soon discover that our greatest uncertainties remain remarkably fundamental, reaching into the very nature of these ancient travelers. The spacecraft that examined Comet Halley, Comet Borrelly, Comet Wild 2, Comet Tempel 1, and Comet 67 Churyumov-Gerasimenko all encountered nuclei that were surprisingly light, fragile, and porous. Their interiors resembled loosely assembled structures rather than solid blocks of ice and rock. But does every comet share this architecture, or have we simply visited an unusually similar group? That question remains unanswered because our sample is still remarkably small. Another puzzle lies across the surfaces themselves. During its extended study of Comet 67 Churyumov-Gerasimenko, the European Space Agency mission Rosetta observed energetic jets erupting from particular regions while neighboring terrain remained inactive. Outgassing, the release of frozen material as gas when heated by sunlight, appeared uneven and highly localized. Differences in composition, layering, sunlight, and internal structure all seem important, yet no single explanation fully accounts for the observed pattern. A future mission has been designed specifically to confront these unknowns, approved during the year 2019 and planned for launch during the year 2029. The European Space Agency mission, Comet Interceptor, will wait patiently instead of pursuing a predetermined destination. It will travel to the second Lagrange point, a location where the combined gravity of Earth and the Sun allows spacecraft to remain in a relatively stable position. This outpost lies about 1,500,000 kilometers, which is about 932,000 miles, beyond Earth, but the destination itself has not yet been discovered. Comet Interceptor will remain ready until astronomers identify a dynamically new comet, meaning one entering the inner solar system for the very first time after spending countless ages within the distant Oort Cloud. Such an object has never experienced repeated warming by the sunday Its surface should preserve materials almost unchanged since the earliest stages of solar system formation. The Japan Aerospace Exploration Agency is preparing another important mission called Destiny Plus, planned for launch during the year 2028. Its target is asteroid 3200 Phaethon, the unusual active asteroid responsible for the Geminid meteor shower. By studying this object at close range, scientists hope to better understand where the distinction between comets and asteroids begins to disappear. But one mystery still reaches beyond every planned mission. The unexplained acceleration of the interstellar visitor Oumuamua continues to challenge planetary scientists. No explanation has gained universal acceptance. Meanwhile, the Vera C. Rubin Observatory is expected to discover many more interstellar visitors early enough that future spacecraft could realistically intercept one. For the first time, we may greet a messenger from another star before it slips away forever. Stand for a moment at the imagined frontier of the sun's influence, and the meaning of home begins to blur. Out there, the distant members of the Oort Cloud drift so far from the sun that its gravitational hold becomes remarkably delicate. They still belong to our solar system, yet only barely. Beyond them stretches interstellar space, where neighboring stars trace their own paths through the Milky Way, and the boundary between one stellar family and another grows surprisingly subtle. At those enormous distances, almost any gentle disturbance can redirect an icy world. A passing star may shift its course by a tiny amount. A giant molecular cloud, an immense concentration of cold gas where future stars are born, can add its own faint gravitational pull. Even the Milky Way itself contributes. The combined gravity of countless stars, clouds, and unseen matter creates what astronomers call the galactic tide, meaning a gradual stretching force that slowly flexes the outer Oort cloud. The effect is delicate, yet over millions of years it becomes profound. But the solar system is never standing still. Together with the Sun, we complete one orbit around the center of the Milky Way in roughly 225 million to 250 million years. During that immense journey, our entire planetary system also moves above and below the crowded middle layer of the galaxy. This region, known as the galactic midplane, contains a greater concentration of stars and interstellar material. Each crossing slightly changes the gravitational environment surrounding the distant Oort cloud. Some researchers have wondered whether these crossings increase the number of comets entering the inner solar system. If more icy bodies are disturbed during these periods, Earth could experience episodes of elevated impact rates lasting millions of years. A few studies have suggested that such cycles might correspond with certain mass extinction events preserved in the geological record, recurring roughly every 26 million to 30 million years. But the evidence remains incomplete, and many planetary scientists continue to debate whether the apparent pattern reflects genuine galactic influence or simple coincidence. Another proposal once captured scientific imagination. During the 1980s, astronomers suggested that the Sun might possess a distant companion star named Nemesis. This faint object was imagined to travel on a vast orbit, periodically disturbing the Oort cloud and sending waves of comets toward the planets. Wide-field infrared sky surveys have since searched extensively and found no companion star within about 1 light year. That is nearly 9,461,000,000,000 kilometers. The hypothesis gradually faded, although it revealed how seriously external influences on comet populations were being investigated. But the larger lesson endured. Every long period comet carries the imprint of forces acting across the galaxy itself. By the time you watch one sweep across Earth's sky, its path has already been shaped by drifting stars, galactic tides, and motions unfolding over distances measured in millions of light years, linking a fleeting streak of light to the architecture of the Milky Way. Long before Earth gathered its oceans, before the planets settled into familiar paths, the material that would become all of us drifted within a vast rotating cloud of gas and dust. Astronomers call this cloud the solar nebula, meaning the birthplace of the solar system. About 4.568 billion years ago, gravity slowly tightened that cloud until the young sun ignited. Around it, the remaining material flattened into a broad disk where worlds gradually emerged over only a few million years. Far beyond the growing planets, the environment remained intensely cold. Here, substances that could never stay frozen closer to the sun became trapped inside newly forming bodies. Water, carbon monoxide, methane, and nitrogen condensed into ice alongside mineral grains and dust. Those frozen mixtures became the first comet nuclei. While the inner solar system changed through relentless collisions and volcanic activity, these distant objects spent most of their existence preserved in deep cold. That preservation makes them extraordinary. We are not simply observing wandering ice and rock. We are examining material that has remained remarkably close to its original state since the solar system itself was assembled. Every measurement of a comet offers another fragment of the ancient chemical record, allowing you and me to investigate conditions that disappeared billions of years before our planet even existed. But some ingredients inside comets are even older than the sunday. Tiny mineral particles, known as pre-solar grains, formed around dying stars and in powerful stellar explosions long before our own stellar family came into being. Several of these grains have been dated to roughly 7 billion years old. They survived the collapse of the solar nebula, became incorporated into comets, and now preserve a direct physical link to an era more than 2 billion years older than Earth itself. Scientists continue reading this history through exceptionally precise chemical fingerprints. Ratios between different forms of hydrogen, called isotopes, along with the abundances of noble gases and many other elemental signatures, reveal the temperatures and environments where comet material originally condensed. This work resembles chemical archaeology, except the artifacts arrive from space rather than buried beneath ancient landscapes. Comparing different comet families expands that picture further. Objects arriving from the distant Oort Cloud often display chemical differences from those originating within the Kuiper Belt. Those variations help reconstruct the temperature and density pattern that once stretched across the young protoplanetary disk, the broad ring of material from which the planets assembled. Each comet becomes another marker showing where within that disk its building blocks first accumulated. But the story may have been reshaped by wandering planets. The Grand Tack model proposes that Jupiter once migrated inward to roughly 1.5 astronomical units before Saturn's gravity drew it outward again. This remarkable journey would have redistributed countless icy bodies, altering which reservoirs ultimately stored different comet populations. As each newly studied comet reveals another chemical signature, we move closer to testing whether that ancient planetary migration truly unfolded as imagined. Imagine the countless planetary systems scattered across the Milky Way, each forming from its own swirling cloud of gas and dust. If those systems also produced vast populations of comets, then the process we have traced through our own solar system may be unfolding almost everywhere. The discovery of the interstellar comet Borisov strongly suggests that comet formation is not unusual. It may instead be one of the most common outcomes of building planets around a star. Wherever those icy bodies travel, they carry familiar cargo: water ice, amino acids, carbon rich compounds, and other complex organic molecules become passengers on journeys lasting millions or even billions of years. When comets pass near young planets or collide with them, they spread those ingredients across worlds that may otherwise have remained chemically poorer. The same deliveries that reached Earth could be arriving throughout the galaxy with remarkable consistency. But the destination also matters. Astronomers describe a galactic habitable zone, meaning regions of the Milky Way where enough generations of stars have already forged essential elements such as carbon, oxygen, nitrogen, and phosphorus, while conditions remain stable enough for planetary systems to survive over immense spans of time. Too close to the crowded galactic center, intense radiation and frequent stellar encounters create greater hazards. Too far outward, many of the heavy elements required for rocky planets become less abundant. Between those extremes, comet activity may accompany countless developing worlds. If amino acids are commonly delivered and liquid water exists on suitable rocky planets, then the basic chemical ingredients for life could be widespread. That possibility has transformed how many scientists think about biology beyond Earth. Instead of asking whether nature can assemble life's building blocks, we increasingly ask how often those ingredients progress towards something far more extraordinary. But one profound mystery remains untouched. No comet can explain the transition from complex chemistry to a molecule capable of making copies of itself. That leap from collections of organic compounds to genuine biology remains one of the deepest unanswered questions in science. Comets may provide the raw materials. They do not yet reveal how those materials awakened into living systems. A glimpse of that uncertainty appeared during the debate over phosphine detected in the atmosphere of Venus during the year 2020. The original observations suggested a molecule that, on Earth, is often associated with biological activity. Later analyses challenged both the detection and its interpretation, leaving the question unresolved. Even so, the discussion encouraged scientists to consider whether comet-delivered chemistry might influence planetary atmospheres as well as their surfaces. Another compelling destination circles far beyond Earth. Saturn's moon Enceladus continuously releases water vapor from a global ocean hidden beneath its frozen crust. Those towering plumes resemble a natural comet that never exhausts itself, carrying water, organic compounds, and chemical energy into space. By studying that material directly, we may someday learn whether comet-like chemistry naturally progresses toward life when liquid water endures long enough. In that sense, comets remain tireless couriers, delivering the same remarkable collection of ingredients across the galaxy, while leaving the greatest mystery still waiting to be solved. Across almost the whole span of human history, a comet carried meaning before it carried understanding. When one appeared overhead, people searched for themselves within its light. Kingdoms expected change. Rulers anticipated judgment. Entire civilizations looked upward, believing the universe had chosen that moment to speak directly to them. You can almost understand why. A brilliant visitor arrived without invitation, lingered briefly, then disappeared beyond imagination. But the story we uncovered is even more remarkable. That glowing traveler was never responding to human events. Its journey had begun billions of years before anyone could witness it. The comet that crossed the skies after the death of Julius Caesar had already existed through the birth of Earth itself. It formed while the young solar system was still assembling, before the planet cooled, before oceans spread across its surface, and before the first living cell began to divide. That realization changes the meaning without diminishing the wonder. What earlier generations interpreted as a heavenly message turns out to be an authentic fragment of the original solar system. Few objects remain so unchanged across such immense stretches of time. Mountains have risen and eroded, continents have drifted apart, entire branches of life have appeared and vanished. Yet a comet can preserve material from an age older than every familiar landscape surrounding us today. But the connection reaches beyond age alone. Within comet nuclei, scientists have identified amino acids, the same family of molecules that living organisms use to construct proteins. As sunlight warms a comet, water escapes from its surface, and that water is chemically identical to the water filling Earth's rivers and oceans. Whether comets supplied only a fraction of our planet's water or a greater share remains debated, yet their contribution to Earth's chemical inventory is impossible to dismiss. Seen from that perspective, the relationship becomes deeply personal. We are not standing apart from these wandering bodies as detached spectators. The atoms within your body and mine were assembled through the same cosmic history that shaped the comets themselves. Both emerged from ancient stellar material, mixed together inside the solar nebula, then followed different paths through billions of years before meeting again in this moment of understanding. The astronomer Carl Sagan famously wrote that we are made of star stuff. Comets add another layer to that thought. They became wandering archives, preserving ancient ingredients, redistributing them across young planetary systems, and perhaps delivering portions of the chemistry from which living worlds eventually emerged. They were not authors of life by themselves, yet they may have served as faithful couriers, carrying essential materials wherever gravity allowed them to travel. But history also reminds us that comets possess enormous destructive power. They have altered planetary surfaces, changed climates, and reshaped the course of evolution. The fear they inspired was rooted in something real. What people misunderstood was the larger balance. The same celestial travelers capable of bringing catastrophe may also have helped prepare the conditions that allowed conscious beings to stand beneath the night sky and finally understand what they truly are. Long after every familiar landmark has vanished, the distant frontier surrounding our solar system will remain astonishingly familiar. The countless icy bodies resting within the Oort Cloud will continue tracing immense paths around the fading remains of the Sunday. Their journeys unfold across spans so vast that the rise and fall of civilizations becomes almost impossible to distinguish against them. Our sun still has roughly 5 billion years of stable life ahead before exhausting the hydrogen at its core. After that, it will swell into a red giant, expanding until the inner planets face destruction. Earth will almost certainly disappear within that transformation. Eventually, the outer layers will drift away, leaving behind a white dwarf, the dense glowing core of the star that once illuminated every ocean, mountain, and living creature we have known. But gravity endures. Even after the sun becomes a white dwarf, its remaining mass will continue holding much of the Oort cloud together. Those frozen worlds will circle a faint stellar ember for trillions of years, preserving their ancient interiors with remarkable fidelity. Every orbit will continue, every frozen archive will wait. From time to time, outside influences will interrupt that stillness. A passing star may drift close enough to alter a comet's path. The combined pull of the Milky Way will continue exerting its gentle tidal influence across the cloud. One object after another will begin an almost unimaginable fall toward the fading Sunday. As each approaches, ancient ice will warm, gases will escape, and a glowing coma, meaning a temporary atmosphere surrounding the nucleus, will blossom once more. Tails will stretch across space again, even if no eyes remain to witness them. But many others will never return. Stellar encounters will gradually hurl countless icy bodies beyond the sun's influence altogether. They will become interstellar travelers, carrying with them a preserved chemical record of this planetary system. Some may wander through the outskirts of distant stars billions of years from now. Perhaps instruments built by civilizations we cannot imagine will notice their arrival and recognize them as relics from another long vanished home. Even now, somewhere within that immense reservoir, one untouched comet has almost certainly begun its inward journey. Nudged by the slow rhythm of galactic gravity, it is descending toward the inner solar system for the first time in perhaps a million years. Its surface has never felt meaningful warmth from the Sunday. Locked beneath its frozen crust remain minerals, organic compounds, and microscopic grains older than Earth itself, preserving a memory of conditions that existed before our planet was born. Its arrival may still lie roughly 10,000 years ahead. Whether anyone stands beneath the sky to greet it cannot be known. But the comet will come regardless, following the same patient laws that have guided it since the solar system first emerged. That is the enduring lesson they leave with us. Comets are not omens, and they are more than hazards or passing spectacles. They are the solar system remembering its own beginning, carrying that memory across time long after every other voice has faded.